So I have a continuous function here. It can be like this, it can be like this, it can be like this. Now observe that if the function takes positive value at some point and a negative value at some point, then it also takes value 0. So if a function has to pass from positive values to a negative value, then it has to cut this x-axis. Okay, so it is easy to see, but like, do we have a proof? That can we prove this? So let's start. So, and to prove this, I'm going to use something called nested interval theorem. Nested interval theorem. Let f be continuous function defined on some closed interval a comma b such that f of a is also, here I will take that f of a is positive and f of b is negative, but you will see that even if I take some other points, that is, if I take some other points here c and d, such that if f of c is positive and f of d is less than 0, then also this same thing will apply. Okay, so it does not matter. So f a is positive, and sorry, here it will be f b is less than 0. F b is less than 0. Then there exists some c inside open AB, so here it is open AB, such that f of c equal to 0. Now, so first I will give you the sketch of the proof, that how are we going to show this. So sketch of the proof is this. So here A, here it is B. Now see, here f of A is positive, so my function will look something like this. F of B is less than 0, so it is here. Now I will look at a plus b by 2, a plus b by 2. Okay, so now I will look at the value of f of a plus b by 2. Now this can be either equal to 0, this can be positive, or this can be less than 0. If this is equal to 0, then we are done. Then we have already found a point which is inside this interval and such that the function value is equal to 0. So we are done. Now if the f of a plus b by 2 is positive, then I will look at the interval. So here, so suppose that this value is positive, this means that function is something like this. Okay, then I will look at the interval this a plus b by 2 and b. I will look at this interval. Now in this interval, this question is same. Now here see, here I will call this as a1 and I will call this same b as my b1. Now here again f of b1 is positive and f of a1 is positive and f of b1 is negative and f of a1 is positive. So, and I will again do same thing. I will take a1 plus b1 by 2. So I will take this. Now here I will look, here if the function value is negative, then I will take this interval. So here now the function value is negative, so here it is a1 plus b1 by 2. So now I will take this interval and again I will do the same thing, and so if I do the bisect it, then it will be here. So I will then, now here the function value is positive, so I am going to choose this interval. So I am going to choose an interval in such a way that this left endpoints, in this left endpoints the function value stays positive and on the right endpoints the function value stays negative. Okay, so and in this way I am going to construct a sequence of nested interval with what property. So here I have ai bi, and the properties are going to be f of ai will be positive for all I, f of bi will be negative for all I, and now you see here I am dividing this interval by 2. So each time I am taking the length by 2. So here the length of, so if I call this as II, then length of I1 is b minus a, length of I2 will be b minus a by 2. So length of In will be going to be b minus a upon 2 raised to n. Here if I put 2, then it's minus 1. So this will, so these are the nested interval with these properties. So this is first property, this is second property, this is third property. Now see, have you seen this definition of the continuity, that if a function is continuous at point, let's say x, then if I take a sequence xn converges to x, this implies that f of xn converges to f of x. So this is an equivalent definition to the epsilon delta definition, and this definition is also very important in real analysis because it is everything about sequences, and this uses sequences. So like if someone asks you that what is the definition of a continuity at a point, then you will say that for every epsilon take, so there exists a delta and so on and so on. But isn't this cooler? So like this thing is more cool, that if you say that take any sequence xn converges to x, then f of xn converges to x, then I will say that f is continuous at that point. So this is more cooler definition according to me, obviously. So I'm going to use this definition in the proof. So by the nested interval theorem, so there exists some C, because now I have sequence of nested interval with this property. So by C, such that C is intersection of all ai comma bi, and an converges to C, bn converges to C. Okay, so now since an converges to C and the function is continuous at C. Now this function is continuous at C, so this implies that f of an will converge to f of C, and also f of bn will converge to f of C. Now see now see that f of an is positive. Why? Because of our construction, because the way we constructed this nested interval, f of an is positive, and this is a sequence of real number which are positive, so it cannot converge to a negative real number. So this cannot converge to a negative real number. So see, because this is very easy, suppose here you have 0 and this is a sequence of positive numbers, so all the things are here, so it cannot converge to this number, because suppose it converges to this number, then I can just choose some epsilon which is very small, then I will have some n such that after that all the terms will lie here, but except for finitely many terms. But this is a contradiction because all the terms are here, so this is a contradiction. Hence a sequence of positive numbers cannot converge to a negative number, but it can converge to 0. Yeah, but it can converge to 0. So this means that since f of an is greater than 0 and f of n converges to C, this implies that f of C is greater than or equal to 0. And similarly f of C is less than or equal to 0, and by this we have f of C is equal to 0. See how easy was it, isn't it? So this is the proof of intermediate value theorem using nested interval. I will also prove some other things in my upcoming videos using nested interval theorem only. Using nested interval theorem, I am going to prove many more things. Rolle's theorem and all these things can be proved using just this nested interval theorem. So I will do that, and thank you for the video.